But I think the microphone is quite powerful, so...
Okay, we don't need to move, necessarily,
yes.
but behind the mask, it can be troublesome. Let's see. Okay, but I'm looking at the face on Zoom and see, okay, it seems okay. Okay. Bonjour tout le monde. Bonjour Miguel. So I have the privilege to be the president of your PhD committee today. Before we start, I would like to introduce all the members of this committee. So I'm Professor Patrick Le Calais at the University of Nantes. In your committee, so there are two rapporteurs who did already some assessment of your PhD. So we have from University of the Florence, so the Firenze, Professor Alberto Del Bimbo.
Good morning.
We have in Rennes the senior scientist from Interdigital, Ngoc Diong. Hi.
Hi. Hello.
We have another country from London. We have the Professor Laura Tony from UCL in London. And hi,
everybody.
We have two invited members in this committee. Ramon Aparicio Pardo, de l'Université Côte d'Azur, and Yuyin Wu, de l'INRIA. And of course, your supervisor, Lucille, and Frédéric. So we are very pleased to hear today what your defense about streaming virtual reality. Miguel, the floor is yours for the next 45 minutes.
Okay, thank you so much. And so first of all, thank you for attending this presentation, either virtually or presentially. So I'm Miguel Romero, and today I will present you my PhD thesis entitled Streaming Virtual Reality, Learning for Attentional Models and Network Optimization. This thesis was supervised by Professors Lucille Sassatelli and Frédéric Precioso. So virtual reality has many applications that include remote education and video conferencing, or to grant access to health services to people in remote areas, to do virtual tours to visit new places without physically traveling there, and of course in gaming, and particularly in cinematography, with more serious applications like some more serious applications that allow us to experience situations from the point of view of other people. So despite all these promising applications of VR, the development of immersive content is still hindered by three major issues. So first, the headset technology is still nascent and immature, and often leads to eye strain or fatigue or cyber sickness. That still has a long way in the development. Second, the design and production of immersive content still faces some important questions. In particular, what is the attentional process in the virtual reality experience, and how it connects with the autonomic nervous system, as the entire body now can be involved. And then, and third, the distribution of virtual reality videos is still challenging. Unlike regular videos, where the streaming now of high quality 360-degree videos is still an unsolved challenge. So in this thesis, we propose several relevant multidisciplinary solutions for these problems. For example, we propose the use of Fourier streaming techniques to reduce the fatigue and at the same time reduce the bandwidth waste. And it's also important to understand the attention mechanisms to provide guidance methods that adapt to the user's motion without affecting their vestibular system. So all these applications are multidisciplinary, and even though they have been historically strongly contributed by one discipline, in this thesis, many areas of knowledge like multimedia, machine learning, and filmmaking get benefits from such approaches. So the contributions in each of these fields, define the outline of our presentation. So first, I will present generally the problem of streaming 360-degree videos. Then, in the block of prediction, I will start by presenting the existing models and our analysis to find the weaknesses and strengths of each architecture, which enable then us to develop new approaches for the problem of head motion prediction. And one of such architectures is TRACK, There is a deep learning model that we propose to perform head motion prediction, and a second model that we call the emoji, that is based on rotational physics. And this is used to study in depth the interaction between the visual saliency and the head motion. So then I will present our streaming system that adapts to the user's gaze to reproduce the human natural focusing process, while at the same time reducing the bandwidth waste. And later I will present a control mechanism that to trigger rotational snapcuts to perform film editing techniques based on the user behavior to better orient and guide the user towards the areas the director wants them to explore. Finally, we will discuss current and future work. So for now, let's start with the introduction. So a 360-degree video is a video that is projected in a sphere, and the viewer can explore it with a headset, and only the field of view, that is the area where the user is looking at, will be shown at this screen. So it's difficult to stream 360-degree videos because rates than 20 degrees. So you can imagine it as 5 separate videos, one in the front, 2 on the sides, 1 in the top, and 1 in the bottom. And since the video is meant to be observed an inch away from the eye, then the resolution of these videos must be much higher. So to ensure good immersion, it is recommended that the pixel resolution of the display viewport must be at least 4K. So the resolution for the full 360-degree video should be at least 12K. So an advantage that has been exploited from some years now is that the user does not watch the entire video sphere as an atomic entity. The viewer only watches this small portion that corresponds to the field of view. So then we can make decisions in like sending in higher quality some regions in space and sending other regions in lower quality. However, then these decisions have to be adaptive and react to the user's state. So a solution then is to tile the video into pieces, the video sphere into pieces, and encode each of these tiles in different qualities. So then the portion of the sphere that the user has access to at each point in time is sent in high quality, while the rest of the sphere is sent in lower quality. But as expected, the world is not perfect, and we have latencies that affect the streaming of these videos. So prediction techniques are employed to avoid this issue. So then the user constantly requests the video segment, but now the server has to predict what will be the future head positions a few seconds in advance, so that it can format the future video segments and send in higher resolution the areas that will be likely looked at by the user in the future. So if the prediction is wrong, it means that the high quality does not correspond to the area which will be shown in the field of view. Then it's problematic because the quality of experience is going to decrease. So let's see now how far we should make this prediction in the future. So if we have several users downloading this content from the same network, then the latency can increase due to the congestion of several users. So a key element for modern systems of video streaming is the playback buffer, because it absorbs the latency and the bandwidth variations on the network. So if we have now a buffer at the client side, then our latency, that is the end-to-end delay between the request of the segment and then the frame being displayed at the headset, it will be systematically increased with the size of this buffer. So meaning that now the prediction problem that the server has to solve is much harder, because we will need to predict further in time. And this time depends on the size of the buffer. So to develop high-performing adaptive streaming systems, it is very important to anticipate the user's head position. So the first question that we asked ourselves is, okay, are state-of-the-art methods able to solve the problem of head motion prediction for these longer time horizons? So we want to perform the prediction of the motion of the head to efficiently stream the video content. So first, let's see what is the minimal amount that we have at the server at each point in time during the video duration. So first we have, of course, the content information, because the content is stored at the server. And we also have the latest head positions of the user that is currently viewing the video, because they can be sent in the request from the client to the server. So some other methods proposing the state-of-the-art consider some extra information. For example, they can keep traces of other users that already watched the video and exploit some statistics from these traces stored per video. So we didn't want to rely on these per video statistics for two main reasons. First, what data do we use if we have a new video for which we haven't seen any trace, any user has watched the video yet? And that's the reason why here we talk about generalization. So some works generalize only for users of the same video, but we want to generalize for both users and video, and now the task becomes much harder. The second reason is that it has been found in the work of Miller and others that we can use the stored tracking data to identify virtual reality users. And this is dangerous because from this personally identifying data, we could collect your medical conditions or your mental states. So this will be the multimodal data that we'll consider, the visual information and the trajectory of the past positions of the users, of the current user. So then we found at the time of performing our study that there is diverse methods to perform the head motion prediction. So we denote them here according to the conference and the year where they were published. So the first thing that we notice is that most of the methods use very short time horizons. And also most of these works use deep architectures. So we will study the existing architectures and the way they perform the fusion of this multimodal data to solve our problem of head motion prediction. So we define here the main problem of any head motion prediction method for 360-degree videos that use this multimodal data. So they are, first, they need to extract attention driving features from the video content. They also have to process the time series of positions. And finally, they have to combine both information modalities to produce the final position estimate. A second particular aspect is that as these two types of informations are time series, then most of the works in the state-of-the-art use deep recurrent neural networks like LSTMs. So a key characterizing aspect of each architecture is the way they handle the fusion of between these multimodal data, the position information and the visual information. So the criterion that we decided to group the different methods is if the LSTM handles the fusion or not. So for example, some works relied only on the visual modality, so not even on past trajectory. So we have the block here of PAMI 18, where the LSTM does not handle any fusion as there is only the modality of the visual input. Then we have the LSTM of CVPR 18 that first creates an embedding of the positional data, but the fusion is handled by a fully connected layer. And finally, we have the LSTM of MM18, ChinaCom, and NOSDAP 17 that handle the fusion. So here we have our first research question. So it's, are state-of-the-art methods that consider two different modalities, the visual and the visual input and the position, are they better than baselines that consider only one of these modalities, only the head position? So to be able to compare all these approaches on common ground, we considered a simple baseline that we called here the trivial static baseline. And we call it like this because we assume for this simple baseline that the user will keep the head still during the whole prediction horizon. So, of course, there exist much more complex methods that use regression mechanisms. However, when we compare all the state-of-the-art methods with this very simple baseline, we found that the performance of this baseline is better than all the study methods in the state-of-the-art. And even when we consider the same experimental settings, we consider the same metrics, the same data sets, and the same prediction horizons. So we found the first answer to our question. All state-of-the-art methods that were studied at this time are outperformed by the simple baseline that considers only one modality and that considers that the user will keep the head still. So if we widen our spectrum of interest, we find the same problem in related context, like a 3D skeleton pose prediction. So in this case, Martinez, the authors of this work, Martinez, Black, and Romero, state that after an examination of recent work, all the state-of-the-art performance is achieved by simple baseline that do not consider head motion, body motion at all. So the framework that we use to perform all this comparison of deep learning architectures was published in the ODS track of the Multimedia System Conference of 2020. Okay, so we found that all the methods considering different modalities do not perform better than this trivial static baseline that uses a single modality. So we will try to identify what are the reasons for the methods in the state-of-the-art that perform worse than this simple baseline. So in order to do that, what we did was to perform what we call the root cause analysis. So if the trivial static baseline is better than all the models in the state-of-the-art, then there is a problem somewhere. So either the problem is in the data that was used for the experiments, because maybe there is no correlation between the data that is used and the future values that we want to predict, the future head positions, or maybe the problem lies in the architectures and the way they use this data. So let's start for now investigating the data. So we have taken some data sets from the literature that we denote again by the conference where they have been published. And here particularly we show the results for one important data set, that is the one from Gutierrez and others, that was published in MMC's 18, where the user's motion is found to be higher. So here we have the error course. Oh, sorry. Here we have the error course for each of the methods. And so the better the method, the lower the curve. So in Dash, we have the trivial static baseline that is still outperforming the best performing model in the state-of-the-art. And then we ask two questions about the data. First, is the position history informative of the future positions? And second, is the visual content informative also of the future positions? So are they correlated? The way we did this data analysis was to define two types of baselines. One baseline, which is only made from the first modality, which is the past head positions that we call this baseline the deep position only baseline, because it's a sequence-to-sequence LSTM, so it's a deep architecture that is aware only of the past user's position. And we consider another baseline which is made considering only the visual content. So after we observe the error curves for both baselines in all the data sets, we can conclude that for short-term prediction horizons that we're considering in the literature, lower than 2 seconds, the level of predictability of the head is very significant, corresponding to this inertia effect and also the low motion that we found in some data sets. So, but then for prediction horizons longer than 2 seconds, the saliency baseline starts to become important. So we can conclude, in other words, that first inertia is significant, and then after 2 seconds, 2 to 3 seconds, the saliency starts to become significant. So in the previous analysis of the data, we found that, okay, we can effectively get information from both modalities. So there is no apparent issue in the data that is used. So then our next hypothesis lies in the architecture, in the way the deep learning architecture handles the multimodal data for head motion prediction in 360-degree videos. So now let's state and analyze the possible structural architectural causes. So the question we start asking is, if we assume now that the method that extracts the saliency from the content is perfect, what would be the best architecture to perform the two remaining tasks? Here, processing the time series of positions and combining the both information modalities. So we selected for this the works of MM18 and CVPR18 as representatives of the architectures in our taxonomy, because they solve each of these objectives differently. MM18 uses the LSTM to perform the combination, while CVPR18 uses the LSTM to process the time series of positions. So then from the performance of MM18 and CVPR18, we can conclude that the building block of CVPR18 is better suited for this prediction, meaning that if the attention driving features are properly extracted from the content, then having a dedicated recurrent unit to extract the features from the time series of head positions before merging this embedding into a subsequent layer with the other embedding of the visual content, it provides better results. And here you may say, okay, Miguel, but you made this conclusion assuming that the saliency extractor was ideal. And I will also remind you that you made this discussion about privacy and availability of data. And the ground truth saliency map is obtained from the statistics of the user. So when we move now to a more realistic case, so let's say now that, okay, we don't address the saliency map perfect, we will use a saliency extractor to get our features. When we do that, we get the results for the configuration of CVPR. This configuration that was before found to be a good choice is not sufficient anymore. The performance of CVPR18, this architecture, is degraded as the saliency map becomes much less correlated with the positions we want to predict. So therefore, it's very important to be able to attenuate this effect with an RNN in the first prediction steps and then give more importance to this visual input in the later prediction steps. So let's take a look now at the model that was proposed to solve the weaknesses that we found in the state of the art. So from the previous analysis, we found that a key architectural element that we should add is a recurrent neural network that processes the visual features also before combining them with the positional features. So this result also connects with the seminal work of Jeudi and others on information fusion from structural RNN. So I started my PhD in November 2017, and this work of Jeudi and others won the Best Paper Award of CVPR 2016. So we studied it because it allows to cast a spatiotemporal graph that describes the structure of a problem into a structure of RNNs that by following well-defined rules and steps. So we defined first the dynamic head motion prediction problem as a spatiotemporal graph. So here we have the spatiotemporal graph of our problem. And then we can define our architecture from it. So we can start from the inputs. We have two, we start here from the inputs, and then we have two loops that define two edge RNN. So we have first a green loop that corresponds to the evolution of the field of view, and a red loop that corresponds to the evolution of the content. And finally, we have what we want to predict that specifies another node RNN for the field of view that encodes the fusion of both encodings, of both embeddings, into the result of the new field of view position. So this allowed us to define the structure, the building block of our model track. So the modules of track are represented by first, a doubly stacked LSTM that processes the content-based saliency map. Second, another doubly stacked LSTM that processes the head orientation input. And third, a doubly stacked LSTM that handles the multimodal fusion. So this building block, then, we embed it into a sequence-to-sequence framework. So in the decoder of the fully connected layers are used to predict the future head motion. And finally, a residual connection is used to force the network to learn the head displacement rather than predicting directly the head position coordinates. So here we show the results on average for three datasets, for MMSys18, PAMI18, and CVPR18. So track is able to outperform all the methods on all tested datasets for prediction steps longer than 3 seconds. And for lower prediction steps, track equates the performance of the best method, in this case is the deep position only baseline. When we compare our model with the best state-of-the-art methods, we have an improvement of more than 50% and reaching even 30% improvement. However, when we compare with the strongest baseline, our performance improvement is reduced. So we then try to figure out why it's reduced. And for this, we decided to evaluate the performance gains per video category. So we found in the work of Anquist and others that we can define several video categories for which we can discriminate different users' behaviors. So we have rights videos like this one, and we consider a video as a right when the camera moves in space. We have exploratory videos. Usually these videos are characterized because there is no single region of interest in the scene, and it's closer to a still image where all the regions in the scene have the same level of attraction. So either all the objects are attractive or none of the objects of the regions of the video is attractive. Then we have static focus videos where there is a clearly defined region of interest in the whole video sphere that drags the attention. And we have moving focus videos where there is a clearly defined region of interest in the whole video sphere that drags the attention, and also that region is moving. So we classified our videos either to be exploratory, where all the regions in the scene attract the user's attention at the same level, and non-exploratory, where there is a single region, it could be the camera motion, that attracts the user's attention. So the real gains of track are on the videos that are non-exploratory. In this kind of videos, track significantly outperforms all the other models and all the baselines. And particularly the gains of track against the second best model, that is usually the position-only baseline. Just against the second best model, we can have performance gains of more than 20% for MMCs 18, 14% for PAMI 18, and 18% for CVPR 18. So this is expected. As for focus videos, the region of interest is clearly defined, and we can this region of interest can be easily identified by a saliency approximator, and the visual input is also highly correlated with the head motion in this case. But the opposite occurs in exploratory videos, where the gains of track become much less significant. In exploratory videos, track performs similarly, sometimes slightly worse, than the deep position-only baseline. Still doesn't degrade so far away as the other methods in the state-of-the-art do. But these results are expected because to identify a salient region in an exploratory scene becomes more difficult. So the patterns of the head motion here are more spread, and in this case yield to saliency maps that are less informative. So in this case, track simply decides to not consider the visual input, and then the performance is degraded because the content does not drive the attention anymore, but still the performance is closer to the position-only baseline, unlike other existing methods. So after observing these results, we know that first, for a single video, thanks to this LSTM, track is able to modulate the weight of the relative importance of the saliency over time in the prediction horizon. And this is important because we know that before 2 seconds, mostly the inertia is important. And after that is when the content starts to be important. But also track is able to generalize and learn proper weights for both modalities not seen. So the results of this root cause analysis and also the method track were published in the Journal of Transactions of Pattern Analysis and Machine Intelligence. And the architecture of track was separately presented in a paper that was published in the International Conference on Image Processing, ICIP, on 2020. So even though we have seen that the structure of the neural architecture has been carefully designed to answer all these core questions that were raised during the analysis of the main problem, the connection and interplay between the head motion and the visual content is implicitly exploited in these methods. So here we would like to make more explicit this connection. And in this case, we could have used some back gradient methods or maybe analyze the weights of track over time. However, we found that to do this, we will need to put some constraints on the weights of the inner layers of track to infer the importance of the different components. So then this task starts to become more difficult. So instead, what we did was to devise a white box model where we investigate what information could be learned from the data instead of going to the architectures. So now I will present this model emoji that stands for head motion with gravitation. So this model is used to study in depth this interaction between the visual saliency and the head motion. So as humans, we have evolved a set of cognitive operations that guide automatically the movement of our head and our eyes to center the relevant locations of our visual field. So during this presentation, we have defined this deep learning model that we call track to predict this function of the function of this mechanism of head motion in virtual reality videos. However, it's important to explain and interpret the decisions and predictions of these models. So in this part of the presentation, we would like to study to which extent can we investigate the inner workings of the deep learning models using a gravitational white box model, and also what knowledge can we obtain from this white box model regarding the connection between saliency information and head motion. So in collaboration with Dr. Dario Sanca, currently in a postdoc in the University of Nuremberg, and Professors Stefano Melacci and Marco Gori from the University of Siena, we worked on the design of a gravitational model to determine the focus of attention for 360-degree videos. So we modeled this problem as a ball that is rotating around a sphere at a fixed distance that is affected by gravitational forces from the visual content. So let's start defining these field of forces that guide the head focus to salient areas in the 360-degree content. We model it as the effect of all the forces from all the pixels in the sphere towards the current point of focus. So then, given any virtual mass, mu here, that comes from the visual features, we can construct the force applied towards the current point of focus. So as an example, let's take this pixel R1, And then in our equation, this part corresponds to show us the direction of the attraction, and this part tells us that the farthest the point is, the lower the force of the attraction. And here we have the actual value of the virtual mass that, from the current pixel that can be extracted from the saliency maps. So then our equation of motion can be defined as a vector product of the field of forces and the current point of focus. So here we can see the equations playing in a toy example. The red dot is the position of the head, and the virtual masses correspond to this white Gaussian shape. So we can see that the head motion follows the point of maximum saliency or maximum gravitational attraction, and we can also observe that it oscillates at the end. So these oscillations can be prevented by adding a friction coefficient, and then lambda will be the first parameter of our model. So now gamma, that is highlighted here, is a function that weighs the importance of the attraction force. So the function gamma depends on the value of another parameter, beta, through this equation presented here. It's highlighted. And we will use this function to control the strength over time. So beta is the second parameter of our model. And note here that the smaller the value of beta, the value of gamma gets smaller and increases slower also. So in our equation of motion, we have two main parameters that we can tweak. Lambda controls the oscillations, that we also call it a fatigue or resilience to move our head in the virtual reality experience. And beta controls the strength of this field of forces. So in the same way we did before when we performed the root cause analysis on the deep architectures, we will start first by using information from the statistics of attention using ground truth saliency map. So we have the result here of track in blue and for emoji in red. And when we vary beta, that is a parameter of the impact of the visual input, we see that when we increase it, our results start to get closer to those of track. So we interpret this as track performing a similar type of time step weight varying function as emoji is doing. So in track, the impact of the visual input per time step is learned, and in emoji, the parameter of beta has to be correctly set. However, if we now change the ground truth again, by the saliency map that is estimated from the content, in this case, we use the moving objects in the frame. Here, the results of track are shown in blue for the ground truth saliency, and in light blue when we have the saliency extracted from the content. And now in orange, we see the results of emoji when we use the content-based saliency. So we observe first that both models increase the error significantly. But even more curious in this case is that the performance of emoji is improved by decreasing now the value of beta, opposed to what occurred with in the case of the ground truth saliency map. So meaning that the lower the impact of the visual input, then the results start to get better. So we decided to study why was this occurring, and for this reason, we again split the videos into the different categories. So we tried different values of beta per video category. Here we show the best value of beta per category, and these figures start telling us that first, the impact of the saliency in the head motion is stronger for static and moving focus videos, while it's not so strong for exploratory videos. And this comes from the fact that exploratory videos are characterized by not having a main region of attraction, so either all of the objects are attractive or none of them is, and therefore the visual saliency extracted from the content is not so informative. And these figures also show us that the function gamma should be modified at least in the first time steps. So after we do this, so on average, the prediction of the average prediction using the previous function of gamma, we had this result. And after we modify the function of gamma to vary per video category and tweaking the values of the parameters per video category, then emoji is able to outperform track when using the saliency extracted from the content. So we can deduce from this that indeed track adapts the weights per time step in the prediction horizon in a similar manner as emoji does, since the saliency map becomes relevant only after a few seconds in the prediction horizon. We also found that by tweaking the values of beta per video category, the visual input is less important for exploratory videos and more important for focus videos. So therefore, the deep architecture should consider also another extra task. So not only handling the varying weights per time step, but also identifying the video category. Meaning that if we consider explicitly this task in the architecture of track, we could further improve its results. So the results of this work were accepted at the IEEE International Conference on Artificial Intelligence and Virtual Reality, AIVR, and will be presented on November of this year. And also we got recently the excellent news that our paper was selected as a candidate for the Best Paper Award in the conference. So now I will briefly present our Fourier streaming system, and here our goal is to adapt to the user's gaze, to reduce the fatigue and the discomfort by reproducing the natural focusing process, while at the same time reducing the bandwidth waste. So in the introduction, I presented some of the hurdles of the virtual reality systems. And we discussed about how the headset technology is still nascent and immature and usually leads to eye strain and fatigue and severe one of the issues caused by virtual reality systems is known as the cognitive overload. And we already discussed about videos where all the objects in the scene are attractive. The cognitive overload comes from the inability of the eye in virtual reality scenarios to blur non-focused, to blur regions that are not attractive for the user. And this produces fatigue and discomfort. So one of the major solutions that is envisioned to address this problem is to rely in foveated rendering techniques. So this technique, what it does is to exploit the radially decreasing acuity from the center of the fovea to the eye's periphery. And like this, we reproduce the natural focusing process of our eyes. And we wanted to use this to also reduce the number of pixels that are streamed from the server to the client. So we developed this Fourier streaming system that reproduces the natural focusing process and reduces the bandwidth waste by making the system based on the fovea headset. So we track the gaze position constantly. Then we make a request to the server, a request of a segment, but we include also this position of the gaze. Then at the server, the video is transcoded using FFmpeg, and we create a video in two resolutions, and a high resolution video that covers the foveal area, and a whole resolution video that corresponds to the whole video sphere. And finally, at the client, both videos are combined to provide this foveated effect. So this work was presented at the demo track of the Multimedia Systems Conference in 2018, and also has helped us to define some future research directions using this foveal area to guide the user's attention. So far we have seen methods to anticipate or to adapt to the user's attention. However, some techniques consist in controlling proactively the position of the head through guidance mechanism. So in this part, I will present the control mechanism that we made for one of such guidance techniques. So this work consists in controlling the user's exploration using dynamic movie editing with snapcuts. So first, drive. So the principle of snapcut consists in directing the user's attention to preselected regions of interest by repositioning the user in a new field of view in a snap. So specifically, the trade-off of triggering or not snaps is not having a snap may preserve the level of experience and keep low the probability of disorientation because the user is free to explore. But a snapcut guarantees that the user will see the field of view that is desired by the director, so we'll understand better the story plot, and also that high quality is displayed in the field of view. So the optimal policy lies in between, where the snap frequency finds the trade-off between these two options. So in this work, we focus on how to adapt the snap frequencies, the frequencies of this snapcut, adapted to the user's motion to maximize their level of experience. So that's why we chose to formulate the reward of the quality of experience as the quality in the field of view penalized by the frequency of the snaps, where the more distant the last trigger snap is from the current segment, then the lower this penalty. So we model this problem as a model-free reinforcement learning, and here we use the principle of learning from expert demonstrations known as imitation learning. And it consists here in supervising the training of deciding whether or not to trigger a snapcut with the trigger labels provided by an offline optimal. In this case, the expert is an offline optimal that produces this, that is used with dynamic programming. So the inputs of our guidance methods, our guidance decision model, the inputs observed from the environment are not the same as the defining the reward, but they are said to be as close as possible to these rewards components. So we decided to use the elapsed time since the last snap and the remaining playback time after the snapshot is applied to account for this relative position in time to avoid having too many snapshots in our method. And then a value that we cannot have, that is the feature overlap that accounts for the quality in the field of view. So notice here that we are using the feature overlaps, but we don't know this information at test time, so we have to estimate this information. So we can use the input from the ground truth, and like this we will have an upper bound for the performance of our guidance decision model, or we can estimate this value of future overlap. So track and past here correspond to replacing in the decision model the input of the future overlap values estimated using our model track, or estimated using past informations of the overlaps. So in the figure here, we present the rewards for different configurations of different buffer size and different penalties. So this is, of course, a preliminary work, but what we show here is that with an imitation learning approach, we are able to outperform some basic policies that either trigger all the snaps or don't trigger any snap. So the results of this work were published last year in the Eurographics workshop on intelligent cinematography and editing. So in this dissertation, we have presented this comprehensive processing chain that is tailored to the streaming of virtual reality videos, and I showed through this presentation that the problem of streaming these videos is multidisciplinary, and we have contributed with papers in diverse fields to help the streaming of to help VR streaming systems with prediction models and optimization guidance techniques to optimize the streaming. So let's now move to the conclusion. So first, to find the best performing method for head motion prediction in the state of the art, we developed a framework to compare all these different methods, and showed that all the studied methods are outperformed by this simple baseline that doesn't consider any visual input and just exploit this simple modality that is the past trajectory of head positions. Then this common reference framework allowed us to identify the major flaws of existing methods in their architecture, their metrics, their prediction horizons, and their datasets. And then we performed this root cause analysis to evaluate the datasets and the architectures, and we found that the lower performance comes mainly from the inappropriate fusion of multimodal data. So then we designed track, that is this deep learning architecture, supported by the concept of structural RNN to perform a proper fusion of the visual data. So we found that track establishes a state-of-the-art performance on all prediction horizons and all the datasets, reaching more than 20% of gains against the strongest competitors. Then we designed the emoji, that is a white box model that is based on the physics of rotational motion. And by tweaking the parameters of emoji per video category, we found that the deep architectures for head motion prediction should consider an extra task, not only handling the varying weight per time step, but also identifying the video category to improve their results. We then developed a Fourier streaming prototype that adapts to the user's gaze by reproducing the natural focusing process and at the same time reducing the bandwidth waste. And we will see that this model is useful to perform future works on how to exploit the foveal area to drag the user's attention. And then we formulated the snapshot triggering optimization problem and investigated possible gains in quality of experience. And this is a preliminary work, but opens new research directions. And so far, we have shown that machine learning approaches are relevant to design online snapshot triggering optimization strategies to outperform different baselines. So before finishing this presentation, let's discuss on possible future research direction. So let's start with these future strategies on control mechanism for attention guidance technique. So we said that this is a preliminary work that suffers from a lot of limitations, but this research line shows a prominent future in the development of network optimization techniques. So there are several directions to improve the current work. First, it's important to study new ways to categorize the trajectories of users, to define new video profiles, and to classify how the video content affect the trajectories of these users, and then use these classifications as features for the snapshot decision process. Second, they consider a quality of experience model for the reward were very simplistic. So future work should determine more accurate models, and also to extend the attention guidance toolbox more layers should be defined. So we have, for example, dynamic Fourier streaming, or slowing down the video, or prevent the user from seeing certain sectors on the sphere. But there is also a possibility of inserting some artifacts that will drive the attention, like the one presented in this patent of Professor Duong, on the addition of a character to incite the viewer to move. So one possible research line that we already started investigating consists in using Fourier tunnels. So here we make the hypothesis that the eye will be attracted by a high-resolution area that moves in an appropriate manner to redirect the attention. So one main issue is to define these Fourier tunnels. So we could do it by hand with an expert, annotating all the trajectories in the most attracting areas per video. But to avoid this, we decided to use the tunnels from the user, to define the tunnels from the user statistics. And for this, we use the clustering mechanism developed by Silvia Rossi, and others, including Professor Silvia Toni, to define the different possible exploration patterns in a 360-degree video. For future developments of head motion prediction methods, we already started also studying the incorporation of attention mechanism into track to enhance the fusion of the data and learn explicitly the variation of the weights for each input through time. Future works should also consider variational approaches with the use of variational recurrent neural networks, or also memory networks, to obtain confidence on the prediction of multiple trajectories, as has been proposed in the analogous task in autonomous driving. And here there is an ongoing collaboration with Professor Del Bimbo for the work of Quentin Guimard, the new PhD student of Professor Sassatelli. Another important consideration in track is the embedding of the visual input, because we know that the spherical shape of the video is incompatible with the regular convolutional layers. And usually what is done is that these layers are distorted to vary to match this distorted shape of the spherical projections. So an important investigation is the use of graph neural networks to create the embedding from this spherical input. And this would extend graph learning approaches like the one proposed in the work of Shang and others, including Professor Le Calais. And of course, there are plenty of other future works that I will gladly discuss with you during the Q&A session. So for now, thank you so much for your attention. And now let's continue to the questions from the jury.
So first round of applause. Thank you very much, Miguel, for this very timely and engaging presentation. So now I will give the floor to the committee members to ask questions and comment also the work and the presentation as your manuscript. So the tradition is to start with the rapporteur and the one which is further away. So I'm not sure. The distance between Rennes and Firenze, I'm not very sure about that, but I would give first the floor to Alberto Del Bimbo, considering that I'm from Nantes. Okay, so
thank you so much.
Alberto Del Bimbo, please go ahead.
I'm not sure that Florence is farther than Rennes from Nice. Anyway, okay. So first of all, congratulations to Miguel for his very good work. I read this work with a lot of interest because it's not common to find a work that addresses so many different issues from different fields of knowledge. So I believe that should be appreciated very much the in-depth investigation that Miguel has done in fields that are quite different one from the other. You know, I appreciated the method, the scientific method he followed, you know, checking these different fields, understanding the contents, analyzing the solutions for the state of the art, and then once he understood the limits of these solutions, looking for something that improves these limits. And then after that, even though results have been satisfactory, he investigated the why of this improvement, and provides explanations of that. So all this process, besides its technical difficulties, it's also the reason why in the end he has proposed and looked for innovative different solutions. So the future work he mentioned, I believe, is interesting and is the results of this very in-depth investigation. This said, of course, the results he achieved are very good. A proof is his publication on part of this work on the Pattern Analysis and Machine Intelligence Journal. Indeed, I would not focus very much on this, but I would like to pose some questions about his future work. One remark I had when I read the thesis was that the methods he compares are methods that have been published in 2018. So 3 years from now. So I wondered whether other methods in the meanwhile have emerged, and if these methods exploit new neural architectures, particularly focused on attention, like, for example, transformers. So this is the first question I have.
Okay, so first, thank you for all the discussion about my work and all the good nice words about my work. And to answer this question is, of course, there is even while we were having these publications, there were a lot of proposed methods for the same task. There were a lot of, and if you search just head motion prediction in virtual reality, there is a lot of methods that try to deal with the same task. One important consideration that I try to make in my work is that most of these methods rely also on these statistics per user. So this is what makes this problem much more challenging. But there is also while we were publishing this work, there is also works in 2019 that I remember while we were getting accepted in transaction of PAMI, the performance of these methods were still lower than this trivial static baseline. So there were still methods that didn't consider this baseline. So this is still shocking. And of course, after we published, there is a lot of people that started to notice that this is not the path. We are doing something wrong. Let's check this baseline first. And after our publication, even recently, there is a publication that cites us and compare against track. And of course, we are open to this criticism, because that's the point of making all this work public, so that people can be able to check what was done, what is the code, how can we improve it, what is the errors that I make. And it's not a personal attack, for example, when we say that these methods perform worse or bad. So the same would happen if somebody finds that my method is really bad compared to a new baseline. Is of course it's open and welcome. And about the question on transformers, yes, there is a very recent method, and this is this one that cites us also and compare with track and with the no motion baseline. The title I don't remember well, but it's similar to your attention is similar to the title of the transformers. Attention is so something about attention. But there is more recent works that consider architectures that were used and were showed really good results in this text translation that also consider time series. So to answer shortly, yes, there is a lot of methods that are being proposed. In every conference, there is at least one section where they discuss about head motion prediction for virtual reality. But the good part is that from what I have seen is that everybody is more aware of these usually simple baselines. Even the position-only baseline that is so strong is really simple to build, but it's really difficult to beat. Even we found a lot of difficulties because sometimes while we were building track, we found that it's really strong, this method. And of course, when you increase the prediction horizon, you start having better results. You profit, take advantage of this of the visual input. So again, yes, there is a lot of methods proposed for this task. Yes.
Thank you for that. So the second is you mentioned the research that you are doing together with people in our lab, considering memory augmented networks instead of LSTM. Well, the interesting feature of these networks is that instead of having a single state that somehow resumes the past, we had a memory where elements of the past can be analytically stored and then read and used. So this results in the possibility of having multiple outputs and outputs with probabilities. So the question is how and when and where in your architecture you believe these networks can improve, if they can eventually.
Okay. So first, for the where, I would say here. For the where inside track, I would put it first here. The variational approaches or the memory networks. After the fusion, you perform this. You add.
Yeah.
Yes, you add this set of layers that then give you multiple trajectories. And so this is where. And when, I guess this is for in which cases would it help, or why would it help? And I would say that it will be really helpful because here we are forcing our network to not make any mistake. We are in our loss, we are telling the network, if you just shifted a little bit, it's totally wrong and you did really bad. And sometimes it's not like this. Sometimes the network can make a little error because the head motion sometimes is really, in the case, for example, of exploratory videos, where the motion of the head is really, it could be seen random. But when we consider multiple trajectories, we could analyze all these parts. And of course, in the case, for example, of exploratory videos, we can see that there is, for example, a lot of objects attracting all around the sphere, and that's what it makes exploratory. But then, if we have these multiple trajectories that cover all the objects around the sphere, then in these cases, I would say that all these multiple path trajectory prediction would help in the case of exploratory videos, much more than in the case, for example, of focus videos, where there is more or less a clearly defined path, and the loss function is exactly okay. You should follow this step. And yes, so it's mostly for exploratory videos to define all these separate trajectories on all the objects that are attracting around the sphere.
Yes, I agree. In the case in which you have multiple potential focus of attention, it could be very useful to have more than one trajectory and so that the final decision could be to send all the frame, or several parts of the frame in high resolution. Yeah, I believe. Yeah, I too.
Yes, and also this relaxation of the loss to have multiple trajectories helps in these cases, because when we are so strict in this kind of video categories, we tell the network, you have to predict correctly the path in this video category, where it's really impossible even for a person to try. When you try yourself to try to predict where the person is going to move, it's almost impossible. You don't know in this kind of videos where it's going to move. And you could give different paths. I would say, yes, it's very likely that it will move like this or will move like that. And maybe there is a main trajectory that I could define, but in general, there is plenty of trajectories. So this relaxation of the loss function is really helpful for this category of videos that account for half of the videos that are in the databases. That is not so. These exploratory videos account for 50% of the video categories in all the data sets.
Yeah, also in the case in which you have multiple predictions with equal probability, this could help to expand the focus of attention, for example, and make smoother the decision of the machine. Yeah.
Yes. And of course, yes, we will also help in this tiled video streaming, because in tiled video streaming, it doesn't matter so much the actual trajectory. It matters more what is the probability that each of the tiles is watched. So then, if we have all these multiple trajectories, then you can say, okay, with this high probability, this tile will be watched, and with not so high probability, this portion of the video will be watched. And for sure, this tile will not be observed by the user in the next few seconds. So then send these tiles in low resolution, medium resolution, and high resolution of quality. So you can also vary the quality according to this multiple prediction, multiple scan paths predict.
Yeah. A final question. In the thesis, you mentioned the possibility for future work of having emotional maps. And you didn't discuss this too much in your presentation because of shortage of time. But I believe this is a very important point, because, videos and also 360 videos are media that provoke emotions. Mm-hmm. So these emotions can be provoked in many different ways. So what do you believe are important? This could, which kind of elements in the video can be important to look for? This could be important both for driving the attention on the one hand, but also on making videos for 360 video for user investigation, so also on the editing part. So which kind of feature you believe we should look for to create with this kind of emotional maps?
So for now, I will disclose this. We are working on studying the emotional affection of people inside the virtual reality experience. So there is you can measure physiological data on the people, like valence and arousal, to detect which objects in the scene are making you feel in a way. So this will help on one side to define better silencing maps that include this information, but also on the prediction of the trajectory is really important, this part, because it's this top-down approach, the top-down approach that is not so well studied also. So far we have studied these bottom-up features that are extracted from the content that are mixed in these silencing maps. But this kind of of information, of including the emotion of people in the virtual reality experience inside our considerations, is very important to study this exact, precise top-down approaches, top-down information. That yes, is true. If there is something that makes me feel good while I'm watching a video, I will very likely look there. And so far it hasn't been studied so precisely. So yes.
So if I understand, you take into consideration the user reaction in terms of valence arousal, right? Or
yes. Yes. So we measure these signals from the people while they are exploring the video, and we explore how this affects the exploration patterns.
Basically, these signals could give, where the people receives positive or negative impression, and how strong is this impression. But probably also analyzing the content of the video, you could extract some emotional features. For example, color is a strong emotional feature. There are lot of studies on the effects of color on people on average. And also there is another element very important, which is sound in video, that is able to drive attention on one part of the video or the other. So what do you think about that?
Slide for this. So yes. So in the way we create, so on one side, emotions can help us to also, if you are relaxed, if the video makes you relaxed, then you will move less. You will experience the video more calmly. So your trajectory in the video will be affected by the emotion that is inspired by this video. We are working on that, and we are really close to a publication on this part, on this analysis of the emotions in these videos, and also about the directional sound maps. There is of course there is already works made by Professor Duong on how to detect the sound, the source of the sound in a video. So for sure, it's another input modality that should be considered in future work. We should consider also how the sound, because of course the sound affects. If there is a sound on my right, I will of course look at the subject. If there is a character that is talking, for sure I will be look at this character. So sound affects a lot, and it's an input, it's a modality that we haven't considered yet, but it's inside our future work. We are already studying how to. The thing is not so easy. It's even just combining two modalities is already so difficult when you think, just add another modality, because more data means more better results. No, it doesn't usually mean that. It may mean that you are increasing the noise inside in your network, so your network may get crazy with more data. So we are studying how to make all this fusion of now more modalities inside for the prediction of the head motion. So yes, thank you for this question, because I didn't include this part in the speech because it was on time that I was finishing. But of course, this is part of our future work, how to study this in the exploration, how this affects the exploration patterns. Mm-hmm.
So thank you for these disclosures. Thank you very much. So this is enough for me. I leave the floor to the other referees.
Thank you very much, Alberto. So now I give the floor to Ngoc Duong in Rennes, my neighbor from Nantes. Okay, please go ahead.
Thank you, Patrick, and hello everyone. So First of all, congratulations, Miguel, for a very nice work, very successful piece of work in the dissertation that I really enjoys to review, to read the manuscript. And I also share the opinion with Professor Alberto de Bimbos about the amount of work you